So I'm still trying to build up the background, the foundation for other chapters, for other sections that we're going to cover in this course. So in this lecture, what we're going to do is we're going to derive the Arclength formula. Assuming the length of a particle's path moving along a path using the Arclength functions. And then later on from the arc length, we're going to build up something from the curvature of a curve for different formula. There are two different formula for the curvature that we're going to cover. All right, so arc length. So for example, so if you have some curve like this, like you have some curve like this, now it's actually very easy to measure the length of this curve if you stretch everything out as a straight line. You with me on that? Okay. Now, what if we don't have that luxury to stretch the curve out into a straight line? How would we measure the length of this curve? And that's what we're going to measure, what we're going to derive to actually measure the length of the curve. All right, so arc length, length of a path. So what we want to know is we want to know how long the curve could be if we stretch the curve out like a piece of string. Long. How long the curve could be if we stretch the curve out like a piece of string. So at this point, obviously, we don't have a formula for arc length. But what we know at this macro level is if you are given 2 points, you can find the distance between 2 points. Right. At least we know that much. Okay. So what we want to do is if you want to measure the arc length of this curve, instead of measure this using the formula that we don't know, let's apply that instead of a bunch of a curve here, we put in a bunch of points. Okay. And we can then connect this point using straight lines. Okay. Now from point 1 to point 2, actually you know the distance between these 2 points. From point 2 to point 3, you know the distance between these 2 points. In a way, the arc length of this curve is approximations of all the little distance together. You with me on that? Okay, so you agree with me. Okay, so the formula now for the arc length is approximated by the sum of all the line segment, the length of the line segment. Assume that you break this curve down to n different points. So for I going from 1 to n, and then for the line segment connecting from one point to another, right? That's the calculation right here. And for the approximations of the arc length, the curve, we take the sum of distance. Now, how would you increase the accuracy of this approximation? The length, right? You could use this notation for the magnitude. That's fine, right? You add more points, how many points would you add? Yeah, infinite points, right? So what you do in terms of mathematical terms, you take the limit of the summations, right? You let n go to infinity. That's what you do for calculus one. That's how they derive the integral, right? They put in a bunch of rectangles, right? They find the area of each rectangle, add all the areas together to increase the accuracy of the approximation. They increase the number of rectangles to infinity. Same idea here, right? To measure the arc length of the curve, you put in a bunch of points. Find the distance between the 2 points, add them up together, increase the accuracy by taking the limits as n go to infinity. So that arc length, instead of the approximation notation, I have the equal sign equal to the limit of the summations, lies the distance of the line segment. For I going from 1 to n, you take the limit as n go to infinity. So by taking the limit as n go to infinity, you go in from the approximations to the equal sign. Okay, but still, this is kind of like the idea that help us derive the Arclength formula. Now, what we're going to do is we're going to zoom in into certain regions of the curve. Let me zoom into this region right here. Okay, so I'm going to take this line, connect this 2 points out and work with it. You okay with that? All right, so on the side here, I'm going to take the line, this line, and I call this L. And this line connecting 2 points. And I have this line and I project this into the X and Y axis. I'm going to have a right triangle. And the base is going to be called delta X. And the vertical line is called delta Y. Right, so delta X is just the change in X, delta Y is just the change in Y. Right, remember, we're talking about the distance between 2 points. That's what we're going to do now. Right. So the formula for the distance between 2 points is actually derived from the Pythagorean theorem, right? So from this right triangle by the Pythagoreans theorem, what do you get? You get L squared equal to delta X squared plus delta Y squared. You remember the distance formula, right? If you take the square root of this equation, you have the square root of x2 minus x1 squared plus y2 minus y1 squared. You remember that distance formula. From Pythagorean's theorem, we take the square root on both sides because it's a length, so that's why we just have the positive component of the square root. So now remember what we are dealing with is a vector value function. And the vector value function depends on the parameter t. You agree with me? Okay. So for the vector value function, there's always 2 or 3 components, depends on the dimensions that you're working with. Let's just assume we just have 2-dimensional keys. That's why we just have delta x and y. If you add in another dimension, you're going to do plus delta z squared. Okay. Now, since x and y depend on the parameter t, then delta x and delta y can be written as all right. So let me ask you these questions. I'm not sure if you remember it, but let me ask you this. Hopefully one of you remember. If you have delta x over delta t, what is this approximated equal to? How about this? If you have this fractions and you take the limit of this fractions as delta t approaches zero, what is this equal to? The what I'm talking about? Uh, uh, right. Not accelerations. You are close enough. So this is velocity. What is the notation for velocity? Before we're talking about right. So position over time, right? This is called the average velocity. Remember. Then you take the limit. What do you have? Instantaneous velocity. What is the notation for instantaneous velocity or instantaneous rate of change? Derivative, right? So instead of delta x over delta t and taking the limit, now you can write f prime, sorry, in this case, x prime of t. You're okay with this? Okay, so this is the equal sign. But now you don't take the limit, you not just yet. If you don't take the limit, I'm gonna write this as approximations. You with me? You're okay. All right, so if you're okay with delta x over delta t is called the average velocity or average rate of change for that matter. Eventually, we will apply. Good. Yeah. All right. All right. Approximation. You're okay with that? Right. So at least I want you to see the connection between the average velocity and the instantaneous velocity through the approximations here. You're okay with that? Okay, kind of. Right. So that I can. It's not. So it is not really related to the triangle. The triangle is there so that the length related to delta x and delta y. Okay. So now I use this formula so that I can connect delta x, delta y to delta t. And that is more. Okay. Do you see the connections there? Good. All right. So delta x now can be approximately equal to x prime of t times delta t. And delta y approximately equal to y prime times delta t. So from this formula, L equal to delta x, square root of delta x squared plus delta y squared. What I'm gonna do is I'm gonna substitute delta x by this formula, then delta y by this formula. Okay. Then I have L is approximately equal to, so there's no longer equal sign because you approximate delta X and delta Y. So you have X prime T times delta T square plus Y prime T times delta T square. Yes. So now at this point, you have, if you square all the terms here, you have delta T square on four terms, right? So delta T square is the common factor. You're okay with that? Right. You can pull out the delta T square, or take the square root of the delta T square. And then you're just going to have still the approximations, right? Square root of X prime T square plus Y prime T square times delta T. So this is just the regular multiplications. So I'm running out of time. I have 2 more minutes. So I just want to mention the next step that we're going to do on Tuesday. Right, so this, remember, this is just for one line segment connecting 2 points. Now you have a bunch of points. What you're going to do is you take the sum of all of this, okay? And then changing from the approximations to the equal sign, what you do is you take the limit as n equal to infinity. And when you have the limit as n go to infinity of the summation, you don't write that. You don't want to do with that. What do? You take the limit and the summation and change that to a different notation. What is the? All right, limits of the summations. Yes. Right here, limit of the summation. We don't want to do with this. It's very complicated. Usually we substitute this notation with something else. Integral, more specifically, definite integral. No. Definite integral from A to B because of the parameter of the square root of X prime of T square plus Y prime of T square. And remember, multiply with delta T. Now we have more points from delta T. We change that to dt. And this is the Arclength formula. Parameter T for the parameter T. So A to B. Okay. Right. Very simple. Even though it looks complicated, the formula looks complicated. It's actually derived from this idea of the length between 2 points. So last time we started talking about Arclength of the vector value functions. And let's say you have a vector value functions in this point. That is the graph of vector value functions, and we want to measure the arc length of that functions. So the idea is that we can approximate the arc length by finding the length of the line segment connecting 2 points when you partitions this line into multiple points. Okay. You find the length of the line segment connecting 2 points and sum of all the lengths together. That's the approximations. Now, to increase the number of the accuracy of the arc length calculations, you take the limit as n go to infinity. Okay, so that's the idea we want to build up on. And then we take out the part of the curve and work with one line segment only. And we say that the line is equal to the square root of delta x squared plus the delta y squared. That is from the Pythagorean theorem. And we did something here, we did some approximations here that delta x is approximately equal to derivative of x times delta t, and delta y is approximately by y prime times delta t. And we make that substitutions into the equations of L. Okay. So this is what we got. All right. So L now is approximated by this formula, which is the square root of x prime square plus y prime square, all together multiplied with delta t. Now, the next step is to increase the accuracy of the approximations. All right. Or find the arc length now. Okay. So the arc length of the curve can be approximated at right. So arc length is approximately equal to the summations of square root of x prime t square plus y prime t square multiplied with delta t. All right, I'm going to modify this formula in a little bit, but that's what we got so far. Remember the formula that we got right here, right? It's just the formula to calculate the length of the line segment connecting 2 points. Okay. Now we add all the lines together, all the lengths together to measure the arc length of the vector value functions. Okay. Now, when you do that, you need to include this index for I going from 1 to n because you want to add all the points on the curve together. Okay. And when you add in all the index, you should have x sub I prime, right, and y sub I prime. So the I is the index, and the index here to indicate how many points you have along. And again, to increase the accuracy of the approximations, what you do is you take the limit as n go to infinity. So the arc length now becomes limits as n go to infinity of the summations for I going from 1 to n of the square root of x sub I prime of t square plus y prime sub I t square times delta t. And if you notice, the arc length now have the equal sign. So arc length equal to instead of the approximation. And of course, in practice, we don't write like this. We don't use this formula to do calculations because it's very complicated to do so. So what you do is you replace the limit of the summations as the definite integral. So this is equal to the definite integral of square root of x prime of t square plus y prime of t square dt. Now for t going from from A to B. So t is the parameter. X sub t is the first component of the vector value function, and y is the second component of the vector value function. So this is the formula to calculate the arc length of a vector value function. Okay. Any questions on the derivation? Yes.
What I just said, because I was writing stuff down, the delta T becomes the dT integral.
Right. Now, because you have so many points, infinitely many points, the distance between the 2 points is very small, so delta T. All right, so now I'm gonna formally write down the formula for the arc length of vector value functions in this theorem. So let R of t equal to x of t, y of t. Right. Or usually what we do is we have f of t and g of t, right? And where f of t and g of t are real value functions, where f of t and g of t are real value functions. And t is the parameter between a and b. Now suppose f of t and g of t are differentiable. And f of t and g of t, or g prime of t, sorry, f prime of t and g prime of t are continuous. Then we have the arc length of R of t is given as. All right, so the notations that I'm gonna use for the arc length is S. So S equal to the integral from A to B of the square root of f prime of t square plus g prime of t square dt. So this formula you have here is very similar to what we derived earlier, because x of t is equal to f of t and y of t is equal to g of t. Does anyone need the lecture notes? You got? All right. So this is two-dimensional case, right? Two-dimensional vector value functions. You can apply similar formula for three-dimensional vector value functions by adding the third component, h of t. Okay. So let's focus. Any questions? Any questions on the Arclength formula? All right, so if you don't have any questions, let me move on to example one. So in this example, in the first example, I consider three-dimensional vector value functions. Again, the formula to calculate the arc length can be very similar to what we have in the box. So given that f of t is equal to cosine of 3t, g of t is sine of 3t, and h of t is equal to 3t. Okay. So we consider f of t to be cosine of 3t Therefore, f prime of t is equal to -3 times psi of 3t. So we take the first derivative of each component of the vector value function because we know that we will use the derivative to calculate the Arclength. Now g of t is equal to psi of 3t, or g prime of t is equal to 3 times cosine of 3t. H of t is equal to 3t, or h prime of t is equal to 3. Then the arc length of the vector value function is so you have s equal to the integral from 0 to 2 pi. So I have 0 to 2 pi because of the parameter t right here. So t is between 0 and 2 pi. So the integral of the square root of f prime of t square, so -3 times psi of 3t altogether square, plus 3 times cosine of 3t altogether square, plus 3 square dt. All right, so the integrand should be an easy calculations, I hope. So you have the integral from 0 to 2 pi of the square root of 9 times psi square of 3t plus 9 times cosine square of 3t plus 9 dt. And you can see 9 is a common factor in the first two terms, and therefore psi square plus cosine square become 1. You have this equal to the integral from 0 to 2 pi of square root of 9 psi square of 3t plus cosine square of 3t plus 9 dt. So you get square root of 9 plus 9 dt. Square root of 18. Or this is t times square root of 18 evaluate at 0 and 2 pi. Or you have 2 pi times square root of 18. Or this is going to be 6 pi of 6 pi times square root of. Right, so 18 is 9 times 2, square root of 9 is 3, 3 times 2 is 6. Okay, any questions so far? Okay, so the formula we have right here for the arc length of a vector value function have a fixed interval of the parameter t, right? So t is going between a and b. Now, what if we vary the interval a little bit and see what happens, right? So when we do that, when we vary the interval of the parameter t, we're going to come up with something called the arc length function. Okay. So now consider the arc length functions of the form s of t equal to the integral from a to t. So instead of from a to b, now you're going to vary the upper limit of integrations. The formula going to be the same, that you have a square root of a prime of u square plus g prime of u square du, right? So now you change the variable for the integrand from t to u. Okay, so that is the arc length functions, right? So it depends on the parameter t, right? So s instead of the constant that we find in the example, now s depends on the variable t or the parameter t, right? So it depends on the length, right? The point that you want to consider, then you may have a different length of the vector value functions. All right, so I want to make the formula a little bit shorter. So let me consider this. This is the vector value functions of the form f of t, comma g of t. Okay, you're okay with this. This is the vector value function, two-dimensional case. All right. Now, when you take the derivative of this vector value functions, you have r prime of t, right? And therefore, you have this is f prime of t, g prime of t. You okay? And we call this the what is the name of this? What is the name of this vector? Tangent vector. Okay, so now you have a tangent vector. Can you find the length of the tangent vector? Right. So how would you find the length of a vector? Right. Exactly. Right. So the length of the tangent vector is this, right? So f prime of t squared plus g prime of t squared. Then you take the square root of that. You're okay with that? Okay. So now instead of writing this square root, what I can do is I substitute the square root for the length of the vector of the tangent vector. It's the same thing, right? And you agree that with that. Okay. So now the formula becomes the integral from a to t of the length of the tangent vector dt. Sorry, u in this case. Sorry. Right, the variable we are dealing with is u. So still this is the arc length functions. Now what I'm going to do with this formula I just come up with is that I'm going to take the derivative on both sides of this equation. So I take the derivative of the arc length function. You okay with that? Okay. So you take s prime of t, take the derivative of that. That means you want to do d dt of the integral from a to t of r prime of u du. So when you take the derivative of the integral, what do you get? Right, right. So this is part of the fundamental theorem of calculus. So there are two branches of calculus, right? Differential calculus and integral calculus, and they are connected to one another through the fundamental theorem of calculus. So this is part one. When you take the derivative of the integral, they kind of cancel out, and you're left with just the integrand, but substitute the value. So this should be the length of the tangent vector, but in terms of t. And you done this using the fundamental theorem of calculus part one. Okay. So the idea here is that for s sub t, which is the arc length function, is measure how far a particle travels along a curve, right? You on the curve, right? You as a particle, you move along the curve, and the movement or how far you travel will be described using this arc length function. Okay. Now, so let me write that down. So here this measures how far a particle travels along the curve R of t. So the arcane functions high up is the distant function. When you have a distance, you take the derivative, what do you get? Velocity. Right. But in this case, it's the length of the velocity in the way, right? So that case is the speed, not the velocity, right? Because you just have the magnitude only. So this is called the speed. So in this case, you have, we use a different color here. So S prime of t equal to the magnitude of R prime of t. It's going to tell you the speed of the particle at a given time t. Okay, so we're gonna put all of this information into this box to make it formal. So let R of t be a vector value function. Let R of t be a vector value function. For t is greater than or equal to a. Then the arc length function is given by, so S of t equal to the integral from a to t of the magnitude of r prime of u du provided that R prime of t is differentiable. And furthermore, I remember we take the derivative of both sides of this Arclength function. So we have ds dt is equal to the magnitude of R prime of t. So let me write instead of S prime, as you see here, I'm going to write ds dt. Is equal to the magnitude of R prime of t. And I will come back to this particular form in the next lecture. So we got to come back to this theorem later on in the course. Any questions? Okay, example 2. I want to find the speed of the particle whose position vector is r of t. This is three-dimensional vector value functions. I want to know the speed of the particle as t equal to 2 seconds. All right, so we want to calculate the speed. That means you want to calculate the length or the magnitude of the tangent vector. So to find the tangent vector, that means you need to take the derivative of each component of the vector value function. So consider r of t equal to t cubed, comma negative e to the t, comma 4t. You take the derivative of the vector value function and you obtain the tangent vector. You get this is 3t squared and negative e to the t, comma 4. Then you calculate the magnitude of the tangent vector. So you have 3t squared altogether squared plus negative e to the t squared plus 4 squared. So you have this equal to the square root of 9t to the 4th plus e to the 2t plus 16. Okay, so that the speed, right, at any given time t. Let me take a note on that. So the speed of the particle at any given time t. Right. But more specifically in this example, we want to know the speed at t equal to 2. Right. So the speed of the particle at t equal to 2 seconds is, right. So the magnitude of r prime of 2 is equal to square root of 9 times 2 to the 4th plus e to the 4 times, sorry, e to the 4 plus 16, whatever that is. Make the substitution, don't even forget about it.
Go out to simplify.
No.
That was my problem, perfect.
I mean, at this point, you can just let this in to a calculator together. the concern or the thing that I want you to know is you know how to use the correct formulas, your simplifying to the correct form of the functions. Any questions?
Exam, do you want to write those considered then the speed of the hard for you can see that in the like if we just like logically flow the word.
So just give me some logical enough that, you know, as for me as the grader, know what are you doing, right? I usually, when I write out a math problem, I always try to present that in a way that as a story. You have the beginning, the middle, and the end, or something like that. But for something like this, you don't have to write out all the details. But you will see in the exam, when we finish lecture 7, where you have, when I give you a problem where you have to include all of the information in one place, like calculate the Arclength, calculate the curvature, which we're going to calculate in a few minutes. Then like the unit tangent vector, normal vector, and binomial vector. When I ask that type of questions, I break it down into, let's say, 10 smaller questions. And in each question, it's just, you know, small calculations so that you can arrive at the answer. So you don't have to consider it and then just give me the logical. But there are some problems that you need to follow certain procedure to arrive at the answer, and you will know exactly what to do. For sure, you will know exactly what to do. Okay. Any other questions? All right. I'm going to move on to another concept of vector value functions called curvature. Okay. So the curvature of a curve, right? So let me give you some intuitive ideas. So the curvature of a curve C. So this is a fancy C. At any given point, is a measure of how quickly the curve changes direction at that point. All right, so look at me. I'm moving in a straight line right here, but one point to another. What is my curvature equal to? 0, right? So there's no direction change whatsoever. Therefore, the curvature is 0 when you move along a straight line. Okay. Now, what if I'm moving like this and suddenly make the turn? Yes, I will, right? But when you make that quick turn, quickly change the directions, then you have a large bend along the curve. You see what I'm saying? Okay, so the next bullet say that if the curvature is 0,
You were walking back with facing this.
uh,
Walking back.
Yeah. So you see, so I'm walking back like this.
You're literally facing us and your side stepping in that way. That's what I'm doing. We're walking side.
Like this.
No, stare.
Okay, I'm staring at you.
Okay, now step. Not for the other one.
Okay, this one?
Yes, then keep moving that way. Is that considered zero as well?
No. Okay, so I'm moving toward you, right? And certainly I make a turn. Is that
That.
okay? Like this? Okay, so yes, it's still zero. Okay, because you don't make any turns. Good?
Yes.
All right. All right, the curvature is zero. Then the curve. So the curve I put in the quote here. It's a straight line. At the point of considerations. Yes. There is, it's not happen slowly as we walk. You see what I'm saying? It's very certain because eventually you can see we have to take the derivative. When you take the derivative, it's instantaneous change. Right. Now, if the curvature, did I answer your questions kind of?
Still just like a point. How can I analyze the curve on a single point?
Okay, so let me go back to the curve that we usually consider in calculus 1. So this parabola, right? So you will see later on that in the next few bullets you will see more. So at every point, consider the tangent vector at every point, right? So how quickly it turned or it moved in the certain directions. Okay, so at this point right here, what is the tangent? What is the derivative equal to? 0. So that is where the curvature is 0. Okay. Good. Okay. So if the curvature is large, then there is a sharp bend on the curve at the point of considerations. Okay, so this first 3 bullets kind of give you the intuitive idea of curvature along a curve. Okay, now the next bullets kind of give you the formula to allow you to formulate the curvature along a curve. Okay, so the curvature measures how fast the tangent vector turns per unit length. So this statement we just wrote down will help us identify right down formula curvature with respect to the tangent vector. Now the sharper the turn, on the graph, the greater the curvature. And the smaller the radius of the inscribed circle. So if you look at this graph right here, you have a curve in red. Right? Depends on the point of consideration, you have a difference in inscribed circle. Okay? So here you have a large band on the curve. Here you have a large band on the circle. And for curvature at this point are very large compared to other points. And when you have a sharp curve like this on the large band, the inscribed circle or the radius of the inscribed circle is smaller. Okay, so now I'm going to use this statement right here. The curvature measure how fast the tangent vector turns per unit length. And I'm going to put that in the definitions. So let the fancy C be a smooth curve. In the plane or in space. Given by R of S, where S is the arc length parameter. Then the curvature is calculated as so you have, so this is the notations, right? Kappa. So it's a fancy K. Instead of this K, I'm going to do fancy K to indicate kappa. It's the Greek letter. So kappa. So let me again follow along with this statement right here. The curvature measures. So you want, when you make the measurement, that means the magnitude or the length. How fast the tangent vector turns per unit length. Right. So this is the rate of change of the tangent vector with respect to arc length. So you have, bear with me here. You want to make measurement, so that should be the magnitude notations, right? Of how fast the tangent vector change with respect to arc length. So we're gonna do dt ds. I'm gonna explain dt in a minute. So capital T in this case called the unit tangent vector. Yep. Before I write down the informations, I'm gonna write T prime of S, right? Where T, capital T, is the unit tangent vector of R of S in this case. You with me on that? Okay. The rate of change of the tangent vector with per unit length. So S is the object per unit object. But in practice, this formula is quite difficult to use to calculate the curvature. What we usually or normally do is that we're going to use the formula given in this video. So if capital C is smooth curve, given by R of T. All right, so you have to be careful with the notations, okay? You're going to go back and forth between S and T a lot here. With the definition. The definition is because the curvature measures how quickly the tangent vector turn per unit length. So that's why you have R of S. Okay. But now the formula we're going to use will depend on the parameter t. So therefore, we're going to write the vector value function in terms of t. Then the curvature is like kappa equal to the magnitude of the unit tangent vector divided by the magnitude of the tangent vector. Again, capital T is the unit tangent vector, and R of T is the tangent vector.
The change in the change in the, like, it sounds like the derivative of t, but. Oh,
Because the unit tangent vector, the unit tangent vector is the first group. Like, to calculate capital T, the unit tangent vector, you need to take the derivative of the vector value function to get to capital T. Now you take another derivative. So this basically the second derivative of R, but the first derivative of T. You with me? So you are right. This is the second derivative. But good question. All right. So we're going to do some derivations to go from here to here. Okay. Okay, I'm gonna move on to the next slide. I need a little bit of space for this derivations. So to show the alternative formula of the curvature we applied chain rule to dt. Sorry, dt ds. That is, so bear with me here. You have dt dt is equal to dt ds multiply with ds dt. So I don't want to say capital T in the dt. So it's a this formula is saying that the rate of change of the unit tangent vector with respect to the parameter t is equal to the rate of change of the unit tangent vector with respect to the multiply with the change of the unit of the object with respect to the oh, so this is calculus one. Now, what I'm going to do is I'm rearrange this formula with this equation so that I can solve for ds. Now dt ds is equal to dt dt divided by ds dt. You okay with this rate of rearrangement? Okay, so dTds by definition is how quickly the unit tangent vector turns with respect or per unit length with respect. Now, if we want to make measurement of this change, we gotta find the magnitude. When you make the measurement on one side, you have to do the measurement on the other side as well. So I'm gonna put in the measurement here. You okay with this? Okay. So what is the left-hand side now? So the left-hand side is the measurement of dTds. By definitions, right here, this is kappa. This is the curvature. So the left-hand side is the curvature. Okay. So the right-hand side is there so that we can derive this formula. But kappa is equal to dTds, the measurement of dTds. So dt is equal to t prime of t. Nothing gets there. So if this is the left-hand side is equal to kappa. I just use a different notations. Now for the denominator, you have the s to t. You see this number? S to t. Remember. Now, if you scroll up or you turn to earlier, this is the formula we're going to use for the SDT. Okay, so the SDT is equal to the magnitude of the tangent vector, not the unit tangent vector, just the tangent vector. and ds dt equal to the magnitude of the tangent vector. Then you have that on the left-hand side is the curvature kappa. On the right-hand side, on the numerator, you have t prime of t. And in the denominator, you have the magnitude of the tangent. You okay with this? So this value right here gives you a number. You have the scale. Okay, so you can pull that out of the measurements for the magnitude. You okay? So you just have 1 over the magnitude of the tangent vector multiplied with the magnitude of the unit tangent vector. Or you can write kappa equal to the magnitude of the tangent vector divided by the magnitude of, right, so the numerator is the magnitude of the unit tangent vector divided by the denominator. You okay? Any questions? Bobby, talk to me. Good. Because you, like, so if you measure this, and then you got like another measurement thing, like, it doesn't matter. If you have, if you have this outside, okay, so this one, this measurement. All right, so in practice, again, we're going to use the formula, the second formula or the alternative formula. That is the curvature equal to the magnitude of the tangent vector bounded by to the tangent vector. Okay. So for the next example, we're going to utilize the formula, the alternative formula for the curvature to calculate the following. So suppose you have a circle center at the origins with radius capital R, then the curvature of this circle is going to be equal to 1 over R. Given that the parametric equations or the vector value functions of this circle is x equal to R of cosine of t, y equal to R times sine of t, for t is between 0 and 2 pi. So given that R of t equal to capital R of cosine of t, R times sine of t. Now you take, remember the formula, kappa equal to the magnitude of the unit tangent vector, derivative of the unit tangent vector, sorry, divided by the magnitude of tangent vector. Okay. So you need the R prime, you need the tangent vector. So this gives you negative R times sine of t, comma R times cosine of t. So you have R prime, you make the measurement on that, or find the magnitude of the tangent vector. You have negative R times sine of t altogether square plus R times cosine of t altogether square. You have R squared times sine squared of t plus R squared times cosine squared of t. So R squared is a common factor. You're left with sine squared plus cosine squared is equal to 1. Then you take the square root, so the measurement of the tangent vector is going to be equal to R. You okay with this? You understand why we get R for the measurement of the tangent vector. So you have the tangent vector, you have the measurement of the tangent vector, then now you can find the unit tangent vector. So the unit tangent vector is capital T of t is equal to R prime of t divided by the magnitude of R prime of t. So you need to form the unit tangent vector because later on you need to take the derivative of the unit tangent vector. So the magnitude of the tangent vector is in the denominator. It's equal to so 1 over r times the tangent vector. That is negative r times sine of t, comma r times cosine of t. Therefore, the unit tangent vector is negative sine of t, comma cosine of t. Then we find the derivative of the unit tangent vector. So t prime of t is equal to negative cosine of t, comma negative sine of t. The next step is to calculate the magnitude of the derivative of the unit tangent vector. And the magnitude of the derivative of the unit tangent vector is equal to the square root of negative cosine of, negative cosine of t squared plus negative sine of t squared. So give you cosine squared of t plus sine squared of t is equal to 1. So you have everything that you need to calculate the curvature of the circle. Right. So the curvature of the circle is so kappa equal to the magnitude of the derivative of the unit tangent vector divided by the magnitude of the tangent vector. This is equal to 1 over capital R. So this shows that a circle with smaller radius will have a large curvature and vice versa. Right? A circle with large radius will have a small curvature. So a circle with small radius has large curvature. And a circle with a large radius has small curvature.